Hello everyone. This is the second installment, or perhaps more appropriately part, of our study in integration by parts. As promised, we're going to take a closer look at this problem and one other. Hopefully you had an opportunity to try this out on your own already. If not, I would encourage you to pause the video and try it out first. As with the last video, you may want to hold off writing anything in red while we take an initial crack at this question. So remember from last class, we're trying to choose a u that becomes simpler when differentiated. And the formula we use when integrating by parts is this one. So with this integral, it's not entirely obvious which one would be a better choice for u. Because if you differentiate e to the x, that doesn't get any simpler really. And if you differentiate cos, that gives negative sine, and that's not really that much simpler either. So we're just going to make a choice and see where that takes us. So let's try u equals cos of x, which means dv needs to be e to the x dx. So du, as I just mentioned, would be negative sine x dx, and v would be e to the x. The derivative of e to the x is e to the x. So now we have the pieces for the integration by parts. Let's put it all together. So this will be e to the x cos x plus e to the x sine x dx. So that didn't really seem to get any simpler. It's just about the same complexity as it was originally. But let's see if we can integrate by parts again and see where that takes us. So this time we're going to pick sine x for u, and we're going to again pick e to the x dx for dv. So then du will be cos x dx, and v will be e to the x. So when we integrate this thing by parts, we'll need to carry through this term again, and we have e to the x sine x minus e to the x cos x. So now it looks like we're in a bit of a jam. We got back to the original integral. And it's possible we got ourselves into this mess by making the wrong choice for u and dv. So let's try picking something different for u and dv from the start. This time I'm going to make the opposite choice for u and dv. I'm going to pick e to the x for u. I'm going to pick cos x dx for dv. So that means du will be e to the x dx, and v will be sine x. So let's try feeding that into the integration by parts formula. We will have u times v, so that'll be e to the x sine x, minus the integral of v du, so e to the x sine x dx. So again, it's not really apparent that there's any simplification here, and maybe all we need to do is integrate by parts again. So let's do that for this one, and we'll be consistent. We'll go e to the x, and dv equals sine x dx. So du will be e to the x dx, and v will be negative cos of x. So at the next step, we'll have to carry this e to the x sine x forward. We will be subtracting e to the x cos x. And we also need to subtract the integral of v du. So that will be negative cos x e to the x dx. That's basically an addition of e to the x cos x dx. So next we might try distributing this negative into each term. So we would have e to the x sine x plus e to the x cos x minus the integral of e to the x cos x dx. But again we have the same problem. We're back to start. That's the original integral here. So is there a way out of this, or do we need to draw straws to see who's going to keep going? It might help to take a look at the bigger picture. Does this arrangement look helpful at all? What if you had to solve for y in this equation instead? Do you see what we should do next? So the trick to solve this integral is to treat this as a variable itself, because we have a repeat on the right-hand side. So if we add this integral to both sides, it disappears from the right-hand side, and then we get 2 on the left-hand side. So we would have 2 integral e to the x cos x dx equals e to the x sine x plus e to the x cos x. And if we divide both sides of this equation by 2, we get e to the x cos x dx equals 1/2 e to the x sine x plus e to the x cos x. And we should probably have a constant of integration. So we did it, and we didn't have to spend the rest of our lives integrating by parts. And now for a much less mind-bending example, we're going x cubed ln x from 1 to 3. So to integrate this one by parts, I'm going to pick u equals ln x and go dv equals x cubed dx. So that means du is equal to 1 over x dx, and v equals x to the fourth divided by 4. So putting these pieces into the integration by parts formula, we go uv, so that'll be 1 over 4 x to the fourth ln x, keeping in mind we still need to evaluate that from 1 to 3. And then we subtract 1/4 integral from 1 to 3 x cubed dx. So we can carry this term forward, and then x cubed would have come from x to the fourth divided by 4. So in total, this will be 1 over 4 times 1 over 4 x to the fourth, evaluated from 1 to 3. So we could switch 1/4 times 1/4 to 1/16, and the rest is pretty straightforward. So we go 1/4, 3 to the fourth ln of 3, minus 1 to the fourth ln of 1, and ln of 1 is 0, so that whole term is 0. And then we're going to subtract 1/16, 3 to the fourth minus 1 to the fourth. So this would simplify to 81 over 4 ln of 3 minus 80 over 16. And 80 over 16 simplifies further, so we could do 81 over 4 ln of 3 minus 5. And that's fairly sufficient, but we could also use our log laws to turn this into 81 over 16 ln of 81 minus 5. So the choice is yours which final form you want to leave it in. I'm kind of partial to this one with the repetition of 81, but this is good enough. So here's a couple questions for you to do. That's it for me for today, and I'll see you next time.